So a consumer advocacy group is concerned about the safety of child seats made by a particular manufacturer. They take a simple random sample of 200 of the 9,000 seats that were made by the manufacturer in a given year. 6 of those seats are found to have safety defects. Okay, which of these is a parameter? Is it the number of defective seats in the sample, the percentage of defective seats in the sample, the percentage of seats made by the manufacturer that year that have defects? C, right? It's the parameter is a property of the population, not a property of the sample. Right? Okay, so this is C. What's the sample percentage of defective seats? Six over 200, which we can, even in our heads, turn into a percentage. 6 over 200 is like 3 over 100, which is like 3%, okay? Okay. What would our estimate be of the fraction of seats that are defective in the population? This is not subtle. Not supposed to be subtle. We have the sample percentage. The sample percentage is a nice unbiased estimate of the population percentage. So why don't we use the sample percentage? 3%. How about 3%? Okay.
So we can always do that, say that the estimated fraction.
That's kind of why we're calculating the sample percentage. We're calculating it to estimate the population percentage. And that's our best guess based on the sample. Well, if you were trying to estimate something other than a population percentage, you might not use the sample percentage to estimate it. Okay.
As long as it's a simple random sample, or if it's like a different kind of sample, can you not?
Well, if you're trying to estimate a population percentage, then you know that the sample percentage of a simple random sample or a random sample with replacement are unbiased estimators. Okay, so they would be reasonable estimators to use. If you're trying to estimate something other than a population percentage, then you probably don't want to use the sample percentage to estimate it. And if your sample is drawn in a way other than as a simple random sample or random sample with replacement, you need to take that into account. So if you're using a stratified random sample and the sampling fractions vary, so one stratum you're taking 1 out of 10 things, another stratum you're taking 1 out of 100 things, you want to take that into account because if you just use the sample percentage, it would be biased. Okay. So what we're talking about in this chapter is really just simple random samples and random samples with replacement. If you have another probability sample design, it's not this simple. Okay, what's our bootstrap estimate of the standard error of that estimate? Sorry? Okay, so our bootstrap estimate of the SD of the box is S star, which is going to be the square root of 0.03 times 0.97, right? Then how do we turn that into an estimate of the standard error? We need to multiply F times S star over the square root of n, right? So F is going to be the square root of 6,000 minus 200 over 5999, right? Times this thing divided by the square root of 200. Oh, it was 9,000? I'm sorry. Oh, 9,000. Thank you. Okay. All right, so this would be our bootstrap estimate of the standard error, starting with the bootstrap estimate of the SD of the box. And what's the largest that the standard error, that sample percentage of defective seats could be? The largest standard error could be. The largest the standard error could be for the sample percentage for this sample in this story. I feel like Robin Williams going, rented lips. Yeah. Right. So we would just substitute. The upper bound would be f times a half over root n. So it's, again, the same factor f, square root of 9,000 minus 200 was 200, wasn't it? Over 8999 times a half over the root of 200. Boy, my handwriting could use some help. Okay, so that's the largest that it could be. So far, so good?
So F is the population minus sample over n.
Yeah, so F is the square root of n minus n over n minus 1. Okay. All right. Again, as we were just saying, all the stuff we've been talking about applies just in the special cases of simple random samples and random samples with replacement. If you have a non-probability sample, none of these calculations make any sense whatsoever. And if you have a different probability sample design, like a stratified random sample, a multi-stage random cluster sample, something like that, these formulae won't be the right formulae. They won't give you the right answer for the standard error, et cetera. It's more complicated. We're not going to talk about that. It's a question. Okay, there's a couple things going on. This doesn't have anything to do with normal, but what you're saying is right. So let me see if I can just repeat the ideas. So the following is true. The normal approximation to the binomial is best when p is equal to a half. That's true, and that's what I think you're remembering. That's because the binomial probability histogram is then symmetric, right? Okay, that's true, but it's irrelevant for this particular thing that we're talking about. Okay, what we're talking about is for what value of p is SD of the box biggest. Okay, and there it turns out that that answer is p is equal to a half. Okay, so that it's this thing that we're using here.